Welcome everyone to this next session of 3D Experience Live, and you guys are in for a treat today. So I know you've heard me and seen
You're
me.
overselling it already.
Oh no, I'm not. Yeah, see, that's what I'm talking about. I don't know if you guys have met Mark Pickering. He's our guest for today, and he's going to talk about welds and durability and stuff like that. And you're in for a treat. And the reason I say that is it's my task today to keep him on track. So so we'll see how many rabbit holes we go down and so forth. But this should be a good chat today. So yeah, thanks everybody for coming and joining. I don't know, Sagar, if you have a slide to show up, any of those images to show up. If not, we can just kind of keep going. But yeah, there we go. So what we're going to talk about today is, what is the life of my e-bike? So we've taken this e-bike story through the whole process of, I started out doing some helmets, and then I did some framework, and then we did some plastics and all sorts of other stuff. So today we're going to talk about some welds inside the model and how we can start to take a look at those kind of durabilities. And Mark, I don't know. I think you're going to shoot for 30 to 45 minutes, and I'm sure you'll have plenty to say. So,
Yeah. Not
yeah.
usually a problem. Me continuously solving.
right. Just pull the virtual plug, right?
Yeah.
But anyway, yeah, we'll turn it over to you, and how long's the life of my bike? So,
well,
thanks,
yeah.
everybody.
So yeah, I started here, and I presume you can all see my screen where I've got that image up of the bike. Yeah, I guess that looks like it. And what I'm looking at here, we'll just use this as a quick introduction. I probably won't spend most of the time talking about this particular model, but bikes are actually quite an interesting one in terms of fatigue, because we've got a lot of, why is that not moving? There we go. We've got a lot of welded structures, and one of the things that we may or may not get to, as depending on how well we get through this material, is doing fatigue analysis, why that is preferential over doing FEA in terms of finding potential problems. But then one of the things that I'd like to look at is this particular approach here, where I've just done, we've got a steel tubed bike, it's welded together with this, I don't know what this sort of bracket thing would be called, but we've got this, and we've got little welds running around at all the sections, and we just do a base metal fatigue analysis of it. And we get a little region here. That's the only region that actually lights up on this particular connection at all. And in here, I've already scaled the contours so that 5, and we're looking at log of life. So 5 is what, 100,000 cycles.
So what does that mean? Log of life?
Log of life,
How do you
yeah.
interpret that?
Yeah, so that gets into a little bit of what the load case will be. So if I come back here into this scenario and we bring up the loads, we've got the fatigue loading. So in here, I've got a particular event cycle, which says I've got one load case here that is cycling through with this signal, and then another load case which is cycling through with this signal, and then another load case which is cycling through with this signal. So in here you can see they all have 1, 2, 3, 4, 5 data points, but they vary in X, Y, and Z. So if I zoom this thing out a little bit, and we go back to the unit loads. So I've got a load in here in X, and then if I switch to Y, we've got a load in Y, and then a load in Z. So these are the basic FEA load cases for which we have just stress and strain within the model. And then what I've done is sort of taken an approach here of, let's assume that we'd actually gauged up this rear axle of this bike, and then we'd done some particular event, driving down the road, going off-road, doing a jump, or whatever it is that you're actually interested in. And then we've tracked that data, and we have a time history of what happens in the X force, the Y force, and the Z force. And so when I go into the durability, and look at this thing, I'm saying, okay, this signal, I actually just typed in these numbers, but it could have been that data trace. And then I'm saying, okay, so we've got the X force on this rear axle. That's all of these frames. And this is what we're calling superposition. So this is going to be applied and is going to multiply by that unit FEA stress. And then I'm doing the same in the Y direction, because obviously recorded X, Y, and Z all at the same time. We've just pulled them out into separate channels. And so here we're just combining each of those channels with the stress value for each of the unit load cases.
So each one of those relates to a different static case over in the simulation tree. Okay.
Yeah. So if I go into results again, we can actually look at those. So yeah, we've got a Z load here with a particular stress on this. We've got a Y load with a particular stress on there. Seems like it's concentrated on this area, so no wonder it's not causing a lot of damage here. And then an X load with some little concentrations around these particular bits. So yeah, just regular static analyses that we've combined together, and that when we then go into the fatigue loading, we're putting these together. So here it's just 5 data points, basically, you know, a sinusoidal curve, fully defined.
And do those have to be like a static perturbation, or can they be like a nonlinear with nonlinear geometry?
So it depends. A lot of fatigue analysis that we typically look at tends to be fairly high cycle. So here we were saying we wanted 100,000 cycles. So if you're repeating something 100,000 times, it tends not to be very nonlinear in the terms of the material. So it does tend to fall into what would be a linear analysis, a linear perturbation analysis. Mm-hmm. As you get into lower and lower fatigue, then you will tend to get a little bit more macroscopic level plastic straining going on. And so to do that, you would actually want to have an analysis that went through one cycle of that and was a fully nonlinear static step. And we've got 2 options here. At the top, we can see, so in this first block, I just made a superposition, which was the X signal, the Y signal, the Z signal with those unit load cases. I could also go in here and do a sequence of frames and then say, okay, we want to, if we'd had, like, if this was, say, a dynamic event, which was actually fully nonlinear and did develop a certain amount of nonlinear plastic straining, we could come in and say, oh yeah, event 1, all increments are all except. And what we're doing here with a sequence of frames is we're defining a loading event, which is a bit like an animation that you'll often see, where it goes, okay, frame 1, frame 2, frame 3, and it's cycling through those to form the animation, and you can see whatever the thing is deforming and putting its bit in. But we're actually tracking that from a damage perspective in terms of accumulating fatigue damage. So we could go ahead and do that, and this is getting now we're getting way off topic for a while.
See, we're not even 10 minutes into it. So we do have a quick question.
Keeping me on track here, not encouraging me to go down. But I will get into this, so we'll carry on down this rabbit hole. It is kind of important. Basically, the theory of what's going on in fatigue analysis can be quite complex and can be quite involved. You know, people spend their academic life just studying this stuff. I'm not one of those people. I'm more of a user, and I want to use the clever stuff that they've done to be able to drive an engineering decision on, should I go for bike frame A or bike frame B? Which one of these seems like the better one from a fatigue perspective? Mm-hmm. Mm-hmm. I do care a little bit about the theory. I do care a little bit about the understanding so that what I do actually works. But I care more about how do I actually put this into the software and use it?
Yeah, yeah. I mean, we know the whole adage of garbage in equals garbage out, but I mean, the software is so good nowadays. Like, as long as you have a good engineering background, and you're thinking about what you do as you go through, it, it can do a lot of stuff that you have limited knowledge on. Um, well, we do have a question from one of the people, and I think you may have hit this. So, can you just directly define a durability case, or you have to define like one of those other cases first, right?
Yeah, so let's hold off on that question just for a
Okay.
little bit, because I want to do this bit first, and then we'll come to that bit second. Okay.
Okay. All right.
So
Carry on. Back on track.
back down the rabbit hole. So what I wanted to do here was, we've seen in here, I just put in this second sequence of frames, and we call these blocks. So we've got a block here, which is the superposition, which is the XYZ combination with these signals. And these signals could have been a data file instead of just typed in. And typically that's what you would do if you had test data. But this superposition, for instance, we could say that that is cruising on road. And this might be like an hour's worth of test data where we've been monitoring the XYZ of what happens with this rear axle going through this, somebody cruising on the road. And then this particular one could have been something different, where maybe this was, let's say, a bunny hop jump. And in here, we've actually simulated it inside the FEA. It's not taken from test data. We could have test data and going through these things, but this is where, as a user, you will tend to spend most of your time is for a fatigue. And this is like, what, 10 minutes in just to get to your first question. You asked about what does log of life mean? Everything repeats. But anyway, so what this is doing is this is defining our history. So we could have like an hour of cruising on road, 5 bunny hops, 25 minutes of off-roading, whatever, something that defines a particular load cycle that we want to analyze for, and we want to define the durability for. So that if we've got an off-road bike, maybe there's less cruising on road and maybe there's more off-roading, and if we've got a road bike, it would be vice versa. But the idea would be you'd set up a particular set of load history. Often it's done for like a mile or for an hour or for maybe the actual design life of the structure.
Yeah.
And that would be all of this history that we're going through is what we will calculate the damage for. This is probably going to complain about being out of date. Oh, no, it hasn't. Excellent. I must have cancelled that. But then when we come into this bit and we said, okay, we're looking at the durability and we're looking, this bit at the bottom obviously lights up the most, but for here, we're just concentrating on the top. And then I said, we set this up for 5 as a log of life. So 5 is 10e to the 5, so 100,000 cycles. Yeah, just remembering my basic math.
Yeah.
So 100,000 cycles is what we're looking at, and it's 100,000 cycles of that fatigue loading that we defined back here. So in this particular case, it was that 5-step cycle in the X, Y, and Z loadings that interacted in some particular fashion. But if that had been an hour worth or a mile's worth of riding, then this would be 100,000 miles worth of riding is what we're aiming for as our design life. And we would look at this from a base metal fatigue and go, yeah, it looks pretty good. That's maybe, what, 6.5 here? Again, in log of life. So we're talking million plus cycles. And this is kind of getting to where I was ending up with is if we actually, you can analyze, because this is just FEA, you can analyze this as base metal fatigue. It's just, you're just applying that algorithm and you're setting it up on here. We do actually have in 3D Experience this Verity approach, which actually looks at the welds, and welds tend to be detrimental to the fatigue life.
Yeah.
And so this is what I wanted to show initially, where, okay, we've done exactly the same thing here. I just swapped out and that included the Verity calculations. And we can see that the life has dropped significantly. And now we not only have this one point that is below 7 is typically infinite life in these analyses, because basically it's just when people stop testing material, because it takes a certain amount of time to do 100 million cycles. But we can see we've got other locations lighting up, so there's more areas of concern as a weld, and now we're dropping down to 5.4, 5.5.
So I have two comments that hopefully this doesn't spiral us into another galaxy. But for one, for those of you listening, be sure to like and subscribe. If you like this kind of content, definitely like and subscribe. And if you hate this content, you don't like it, still like and subscribe. And leave us a comment. Right? So let us know that this, we can present what we want to do all day long, but this is this is for the audience, and if there's something we're not showing you want to see more of, please let us know. So this log of life value, if I remember, so it's like a log-based 10 criteria. So if I have 10 to the x, that's what that number right there represents. That number right there is the x. So if I really want to understand the cycles, I do 10 to the x. So I do like 10 to the 7 or 10 to the 5, and that will show me what my number of cycle predictions happen to be, right?
Yeah, and this is maybe a little bit of an artifact of the way that people who study fatigue deal with this.
Yeah.
With fatigue, because you're typically looking at very long lives, you're interested in 1 million, 10 million, 100,000, 10,000. Plotting those out on a graph in true scale, you just get swamped by the end. But you're actually interested in how it develops over those orders of magnitude.
Yeah.
And so they tend to look at it in here. And so because a lot of that comes in from the theory, this tends to be the default way that we tend to look at it. But you're right, 5 here is 10 to the 5, so 100,000 cycles. Yeah. Getting to 6 on this green level is 1 million cycles, and 7 then is 10 million cycles. Okay. So that is the way to think about it, and each of those cycles is that fatigue loading you defined.
Cool. Okay, back on track, out of the death spiral.
Yeah. And where was it? Okay, so this was the first thing I wanted to say, and we probably won't actually, but we might get to this about why welds are bad. If this is a particular interest, the main takeaway here that I want to provide is just there are techniques in the software which will take into account the damage changes that having a weld in the structure does, and they do reflect what is actually going on in the practical sense. And it's a little bit of a word of warning that if you have got a welded structure and you're just using a base metal fatigue algorithm, first, I admire that it's good. It's definitely better than just doing an FEA and just looking at stress. But secondly it's not quite the whole picture. You're still missing a change in the damage mechanism that goes on with welds. But there is software that can do that, and coincidentally, 3D Experience is one of those softwares. Now, that's kind of the wrap-up of that first bit I wanted to do.
Yeah.
And then I said, we'll leave that question and be the second point, and I've forgotten what that second point was.
Surely you hit it already, so I think we're good.
Are you telling me you've forgotten it as well? Oh, dear. Oh, it was about setting this up. Okay, yeah, let's do that. Let's do a bit of setting
if you have to set up some sort of simulation case beforehand.
Yeah. So the first thing I'll do, again, we're sort of skipping a lot of stuff here. One of the nice things about the way that fatigue is handled in 3D Experiences, and I mentioned at the top a little bit about the theory can get quite complicated, The concepts involved can certainly get quite involved. And then I sort of said, I'm more interested in a user perspective.
Yeah.
And the main thing that as a user, apart from setting up the load history, the main thing that you need to be aware of is there is a material database supplied which has fatigue properties in there. And that can be a little bit surprising for a lot of Abacus users, because historically Abacus has been very much just the finite element framework, and people had to bring their own material data to it and populate a material library. With fatigue, there's just less generally known information about fatigue, and certainly less information about representing it, and less information about representing it in a strain-based approach, which is one of the things that FE-Safe and 3DEXPERIENCE have, which we may or may not get to later. But the nice thing is, from a user perspective, if you load up that library of materials, it will have the classic elasticity, the Young's modulus, the density.
Wow.
But then if we scroll down here, it will have what has been a kind of predefined, seems to be the best way of representing that material based upon the fatigue expert's perspective. And often it will be something like this. So we go into the FE-Safe durability. In here, we can see that we're doing a Brown-Miller. We're not going to worry about all these details. The key bit I want to get across is just that the algorithm that we're using has been predefined, and then the coefficients that define that use of that model have been predefined and populated in here. So from a user perspective, all you need to do is use that material in these parts. So we can see here, there's that material being used in this base tube.
Yeah, and you know, I have to plug really the power of 3DEXPERIENCE right here. There are so many things that we get in 3DEXPERIENCE as simulation users that you know, they were put in there with simulation in mind, but really just the whole database of this concept of one source of truth, you know. So with other software, you know, you have to import the material and you have to recreate the material every single time or what have you. But like here in the database, there's one material and everybody gets to use that same material, and you don't have to go in and recreate it. And that, I mean, that works for everything in the database, but materials in general, it's super nice and really powerful. So then you don't have like 40 70, 75 aluminums out there in the database, and you're like, I don't know which one's mine. I'm going to go ahead and recreate another one. You can just use the one that's been put in there and you know, start using that. So anyway, all right, carry on.
As well, from coming from an Abacus perspective, as well as other FEA software, which typically is unitless, just the fact that you're working in a unit system and you don't need to care about that because the material has got a particular unit system in here.
Yep.
And the program does the conversions on the fly that it needs to if you're working in imperial or if you're working in metric or millimeters.
Yep.
That is just really nice.
Yeah. And you can even, you know, so the base units of 3DEXPERIENCE are SI, right? So that's the base units. But then we have our, what I refer to as display units, and you change those into preferences. So if you want your display units to be inches or your display units to be millimeters, you can change that in your preferences. But if I'm working in my millimeter display units and I know something's in inches, I can just type that in and say inches, and it'll automatically convert it to millimeters for me. So there's all this smartness going on behind the scenes with units. And yeah, so for the unitless world out there, it's a huge game changer. For us that are used to working in CAD packages, we're like, yeah, well, whatever.
Yeah, blatantly obvious. Why wouldn't you do that?
Yeah. All right.
But yeah, so what I wanted to do is showing, okay, let's get into a bit about how as a user do we set up a durability analysis. So I've got here what was a solid model that I've mid-surfaced out. And then I've used line fasteners here inside 3DEXPERIENCE to connect these together. These are the sort of purplish elements. And if I do a free edge plot, we can see it's fully connected. So we've got an attachment tube. We've got a base tube in red. We've got this abstraction to a loading point up here, which is where we're going to put a load in to then stress this structure up. And then we've got the line fasteners representing the welds here to go in here. And then what I'll do is I'll come in. And so here I've got a physics simulation. And in this physics simulation, all I've done so far is set up the FEA. So if I come into here, we can see that I have got, where are we? I've got actually, so talking about what you mentioned before about does this need to be a linear static or can this be linear static? I actually have in here a XYZ unit loading situation of a linear static perturbation set of load cases. And then I have what we're currently displaying, which is potentially the non-linear, but is actually just, you know, we're applying 4,000 pounds force here, and then that's going to create a twisting and a shear motion in here, stressing this up. And so if I go into this, we can see, okay, so this is our stress and strain, or our stress plot. Mm-hmm. And in this particular setup, yeah, we're lighting up this sort of free floating section first, more than the other sides. But we can see that because of the weld, we are tending to concentrate. We're tending to concentrate on this corner with a little bit of a concentration on this corner. So that's our. So
you're just creating a regular simulation case.
Yeah,
you're just creating a regular case and you're putting that into the durability.
Standard FEA, static step, nonlinear geometry, all defaults basically setup. So if I want to look at this, and we sort of said already in that scenario, okay, this is our applied load. Now, one of the things in durability is you need a cycle of load. If it was just literally, we have this structure and we push on it with 4,000 pounds force, and then we hold 4,000 pounds force forever, there will be no fatigue damage. It needs a cycle. So the site, and that was kind of what we were showing before with that superposition and the sequence of frames and then the blocks and building up a really complicated potentially cycle. Here we'll just do what is sort of the classic durability people's approach of fully reversing. So 4,000 and then minus 4,000. So we're cycling back and forwards, creating damage as we go through. We don't need to analyze the minus 4,000 if we assume that these are sort of linear enough that minus 4,000 are just minus 1 times this. If they were not the case, like if there was something like maybe a contact patch that comes in, then yeah, we could have a push 4,000 forwards and then a pull 4,000 backwards and do that as a sequence of frames. But for right now, we'll just take this idea and just say we want to cycle this plus or minus 1 of this 4,000 load case. So how do we go about that? Whoops.
We have a really smart question. I don't even know what this is, but can we use Wöhler curves?
Yes, and that's kind of the bit that I've already skipped because we got derailed down this rabbit hole already. So Wöhler curves, they actually, let's see, shall I skip into it? This is kind of important, I guess. Yeah, let's skip into that.
Everything's important to you.
Yeah, that's maybe true. It's important to me, my thinking of it. One of the things that I like, this comes up not necessarily. I guess the first thing to do is just answer the question. The answer is yes, you can, basically, simplistically. But now I want to do what I usually do, which is expand upon that to a painful degree. So the way that I often think about fatigue, and this is getting into approaches of fatigue and where one benefits and one is pros and cons of each, basically. And the way that I like to compartmentalize that is actually by looking at the history of fatigue. And we're not going to look through the whole history of fatigue here. We're going to skip through a couple of little bits quite quickly. But one of the first things back in the day, people just used to believe if you could have something and you could pull on it, they knew you could eventually break it. So just a uni-axial one pull kind of ultimate stress situation. And then the belief was, well, if you're not at that load level, you can keep repeating it forever because it only breaks when it reaches that critical load. And Albert was one of the first people to actually go through and look at this. And he was looking at chains on mining equipment where they're lifting up and dropping down, you know, cartloads of coal or iron or whatever they're mining. And he realized that chains were breaking after a certain amount of time while never experience a load that was as high as that critical ultimate load that they could carry. And so he developed a rig like this, and he started testing chains at different load levels, and he started coming out with this. Now, this isn't a Waller curve. This is specifically for a chain, but it is kind of the first case that we have where people are realizing fatigue is a thing. It's a definite damage mechanism. And most importantly, it's a damage mechanism that occurs at load levels that can be significantly lower than the ultimate applied load that a structure can take. This is great, but it only works for the chain. It only works for the chain that Albert was testing. If you had a different chain, you would have to do all of these tests again to then work out what would be the applied load and when you should replace that chain before it fails in fatigue. And that's the pros and cons I'm skipping through here. Unfortunately, in the history of fatigue, a lot of things occur because of accidents. And this was the Versailles rail accident, which was the major accident that occurred in France. And I think was probably the worst rail disaster ever at the time. But this kind of incident, and we're talking here, we're like back in the 1840s when this occurred, but this is when Waller started looking at fatigue and started trying to come up with what was happening here. And this is the Waller curve, or what is commonly known as the SN curve, because we've got stress amplitude on the left, and we've got number of cycles on the right. And this is basically the approach to fatigue that most people encounter when they first go into this. And this is what we would call a stress-based approach. And the reason that I mentioned about this rail accident is it's important to realize that for this Waller curve, he was interested in failures of rail axles. And those obviously keep rotating as they drive along, and they're driving along a lot of miles. And so typically what he was interested in is this higher level section, the 10 to the 6, 10 to the 7. And the main thing that many people have sort of picked up on from the Waller curve is this concept of the endurance limit. And the idea is here, if your stress is below ultimate, you will get fatigue damage. But if your stress becomes below a certain level, then there is no more fatigue damage accumulated. And so you get this flattening here and you go to conceptually infinite life. It's a little bit arguable about whether that really is there or whether this is just a case of people would test to 10 to the million, but they, you know, if that took them 10 months, they're not going to spend nearly 10 years just to find out if this curve goes a bit further down. So they probably just sort of did that. There is theoretical ideas that an endurance limit should exist because there is a certain amount of stress where even with the stress concentrations at crack tip, you're just not going to get to a level where you're growing any crack that is there. So it is kind of a testing bias, but also kind of a real bias. But the thing that I'm concentrating on is Waller's looking in this very high cycle fatigue range. Mm-hmm. And this is the approach that he took. And where he really pushed the ball forward from, forgotten his name, from Albert, is looking at stress. So instead of looking at the component, he's looking at the stress in a local region on the component. And that's very helpful because even though he was looking at a railway axles and that was what he was concentrating on, we can determine the stress locally on a wide variety of components.
Yeah.
And so where Albert was like, well, I've got this curve, but if you're not doing a chain and it's not the same chain as I've looked at, it doesn't really help you. Here, so long as you can get to a stress, you can then use this material data and get to a fatigue life. So that was great.
Yeah. So this is all about high cycle fatigue. What about low cycle fatigue?
Yeah, and so that's where we get into my cons. So
all right, there you go.
The pros are great. One of the things to bear in mind is this approach of use, and there's various modifiers you can do for mean stress and other things that over the years people realized influence stress as well, which do tend to be included. This is the stress-based fatigue. It has been very common in fatigue analysis programs, including things like SolidWorks simulation uses a stress-based approach. And you can do that in 3D experience as well. The drawback, though, is it was really focused on long life failures. And when you get to shorter life failures, oh, hang on, I've got some other stuff here. So what was I doing? Yes, this is just a little bit of extra stuff. These are all variations or manipulations of the stress-based approach to take into account different things, some of which are better or worse than others. But where I want to get to now is FE Safe. And FE Safe was not the first people to, or Safe Technology were not the first people to do this. They were the first people to put it into a commercially available fatigue analysis program. And there's really two things that they based this on. One is multi-axial loading or multi-axial response, and one is strain-based. So what are we talking about here for strain-based? So this comes down to, if we think about you're looking at the component for Albert and his chains, and then for Waller, we're thinking about looking at the stress on a railway axle, but could be the stress on anything. That's the stress-based approach. But you're looking at that macroscopic level of the structure. And fatigue damage occurs at the microscopic level of the crack itself. And what happens is that in order to accumulate fatigue damage, and this is getting into that endurance limit kind of idea, is at the crack tip, there needs to be enough stress generally that when you look at the crack tip with the stress concentrations of the geometry of the crack tip, it will cause plastic deformation at the crack tip, which then is a permanent extension of the crack that then is what is helping that crack grow. But we're not looking at the crack tip there. We're looking at the macroscopic level of the stress of the structure. And this is where we now get to strain life approach. And these were developed in the 60s. Basically, people were looking at these in a university academic environment. And it was this work that was then brought in the 90s in FE Safe as a commercially available product. But the general idea is if you're dealing with low stress ranges at the crack tip, and we're just sort of showing a localized stress strain curve for the crack tip, you're probably just going up and down this part of the curve. And the majority of the strain that is taking place is elastic strain. You'll put it on, it'll come down. As you get to higher load levels, which still are low in the macroscopic level, you know, there's still linear elastic stress on a element size basis. But at the crack tip, what you're seeing is the stress concentration effect. And so there becomes more and more domination of the plastic straining at the crack tip. And that's what this green curve is sort of showing, is if we break this curve down into elastic portions and plastic portions, we now have these two curves that come in. And this is kind of handy. The actual, what we call strain life approach is not just strain life. It's not just the strain curve. It's the combination of the strain and the stress. And at high cycle counts, this is dominated, the actual life of the component is dominated by the stress life approach. So that's where Waller's curves work really well. If you're doing high cycles, that's great. As you get to lower cycles, and this is representative, this is an actual real data just before anybody takes this too far. This is just sort of conceptually showing the general concept.
Sure.
But as you get to lower cycles, the strain portion of it starts becoming influential. And as you get to lower cycles, the strain portion becomes dominant and the stress portion becomes insignificant or relatively insignificant. And this is what the strain life approach is. Yep, you had a question.
Cool. Yeah, well, just a comment. We have maybe about 10 minutes left. So 5-10 minutes. So if there's some super important topics that you want to get out there, let's be sure and get those out there. And then for the listeners, again, just a general reminder to like and subscribe. So because that's what we're supposed to say on the YouTube. So.
Yeah, and I'll put that one back up again. One of the things that comes up here is when people start hearing about strain life approaches or stress life approaches, obviously the intention then is, or the question then is, oh, do we need to be analyzing the FEA differently in order to use this? And the answer typically is no, because what we will do is in a stress-based fatigue approach, you would do an FEA, you get the element level macroscopic stress of the structure. When in the strain life, we're looking at the crack tip, what we will typically do is a plasticity correction of there. So if this blue is the macroscopic level of stress, it will then correct that to be the crack tip level of elastic plastic stress. Typically by something like, there's a variety of ways to do this, which again, we're getting into theory rather than practical application. So rather than, I'll just sort of say there's a way of doing these, there's alternative ways. FE-Safe uses generally the Neubers rule because it tends to be the most conservative and does match up with practical tests that we've done. But what this means is, because we're doing a plasticity correction of the macroscopic level finite element stress, you don't need to do anything differently. And that's where I was getting to here with this particular approach is, if we're going to, in here, we've got a stress and strain response for this static step. If I want to set it up as a durability analysis, I can just come in here. We've got our FEA analysis case. So we will create a durability case. And then we've got our initial conditions, which is basically a global surface finish. We can either keep this as default, which is mirror polished, or we can choose a particular set of machining. We have our output requests. We have our durability step. But then and you can see here in the durability tab, that's pretty much it. The only thing we're missing is algorithm override. Is if you want to use something different than the material that was set up here that we showed earlier, you can actually override it in here and say, oh, like the question was, can we use an SN curve? Well, if you set up an SN curve, you can, as an algorithm, you can use this algorithm override to choose that instead of the default strain life approach. But then the other thing is just the fatigue loading, where we go in and we now say, what is our history? And we're going to say, because we were just doing a +1 -1 reversal of this static step that we had in the FEA, we'll say we're going to do a superposition. We're going to, as it prompts us, right click and say, add in the static step, which was the applied load we have. And then we'll just give it a signal value of 1 - 1, which is the default, because traditionally in durability, this is like the simplest fatigue durability cycle you can have. So fully reversing +1 to -1 of that. And that's it. We're all set up now to do the durability analysis.
That's it. I mean, that's like,
yeah, this is like the
45 minutes to show me 30 seconds of how to set up a
I
durability.
told you were overselling it right back at the beginning.
I'm glad you. Maybe we should have done that at the beginning and been like, all right,
We're done.
Enjoy the rest of your day.
Yeah, it's one of those things. In one sense, it's really nice to demonstrate this because it's so straightforward. In another sense, it's really problematic to demonstrate this because it looks like you're not doing anything. All of the cleverness takes place in the choice of this algorithm, basically. Like I just went through the history there of Albert and his chain-based loading and the component, and then Waller and the SN curve, and that's used a lot. And then you can do all sorts of things with mean stress corrections and things like that.
Yeah.
The vast majority of all of that is set up just by the material definition. Yeah. And you have an expert who does that once, either uses the library that comes and just accepts that, or for your particular material, we use a library and then say, okay, for this material, we believe any one of these fatigue algorithms is better. And we can see in here, I think we've got stress. Yeah, so we've got uniaxial stress life. So you can do things in here. So you can start setting things in, Goodman mean stress corrections. Some of these are going to be, if you're not an FEA, if you're not a durability fatigue person, this maybe doesn't mean a great deal. But if you have an expert who says, we don't actually agree with what the Dassault people have chosen as the default, or we've got a material and we want to do it this particular way, they can set it up here. But once they've set it up, you're done. You just pull it in as any other material. And then it's just sort of practicality of, define your load history, which can be as simple or can be multiple blocks. Like I've seen people do load histories that are incredibly complex, combining in together different root cases of like if we imagine a car going around a ring, you could have like a fast driving, harsh braking, harsh acceleration, gentle left curve, gentle right curve, sharp left curve, sharp right curve. Those could be your components, and you could build them together in a sequence to make pretty much any circuit in the world. And you may well have a load history that is the Nürburgring or Brands Hatch or whatever, and it's just different combinations in different ratios of those core cases. So you can create really complicated loadings off this idea of blocks and then particular bits. But yeah, from a usability perspective, once you've got the loading and once somebody has identified what the best fatigue approach is, that's great. The last bit that I'll sort of get to, assuming we have a few minutes here, is
just a couple minutes. I do like to end a little bit before the hour because I don't know if you're like me. I don't like it when I'm running from meeting to meeting to meeting. Sometimes I like a few minutes before my next one starts. I'll give you a couple minutes here. So let her rip.
The last thing I wanted to show was, I mentioned about what we've set up here is a base metal fatigue. The material itself is base metal fatigue characteristics. I mentioned back at the beginning that welds behave differently. So the question then becomes, well, how would I set this up for a weld analysis? And I'm currently in this durability analysis case, which is base metal fatigue. What I typically do for welds, and what I did for that bike, is I will duplicate this analysis case. So we'll call this one the Verity one. And if I just expand these, we'll see it already has the surface finish, the fatigue loading that if we define the output requests, etc. The only thing I need to do differently here to say, hang on, we've got these welds in here as line fasteners. I want to analyze these differently to just base metal fatigue. The only thing we need to do is come over here and say this weld fillet set. And then it will prompt us, okay, what do you want to use as the weld fillet? And we'll just go back into the model. We'll expand this connections, which is where I put the line fasteners themselves. So as I mouse over these, you can hopefully see this highlighting. So we've got the one closest to the load, and then we've got the one furthest away from the load. And then we say, okay, we don't need to worry about this when we've got particular things, but there are things you can do about resolving toe failure versus root failure versus some other things. But for a setup like this, where we're just using a line fastener, we can ignore that. At the moment, we only have the Verity approach for these. With welds, we are looking at either steel welds or aluminium welds. And then what is the percent chance of failure? So 50% chance is the default, or -2 sigma or -3 sigma. And then we can pretty much take all the defaults for the rest of this. This is probably one of the more important ones. We're looking at toe failures. We didn't get into this, but typically on a weld, particularly a well-sized weld, it will fail at the toe. So that's the default which is on. And we do OK. And we can see that comes up in our interaction here. Obviously in here, I only have these two welds, but in a more complicated structure, I might have a whole set of them I want to go through. So I could build up lots of weld fillet sets using them. But this is it. I am now once again ready just to look in. And if I look at the results here, we'll see the same thing. Here I set one up for a Verity at 2% failure. Yeah. Same idea of 5, so 100,000 cycles. Remember, it's the log of it, or log 10 of it. If 100,000 cycles is our limit at 2% failure, we're okay, but close. If I swap to 50%, the default, yeah, okay, now we're at 5.8. And if I swap to base metal fatigue only and look at the log of life, okay, yeah, these were all over 6. So even though it highlighted from the FEA case, we knew this was kind of the critical pair of corners. From a base metal fatigue, we're looking, well over 1 million cycles. As we include welds and as we include, less acceptance of failure, we do bring this down, but we can still assess for this structure, for that loading of fully reversing 4,000 pounds force, would this live for 100,000 cycles? Yeah, probably. Certainly if we were allowing a 50% failure rate, almost certainly. Yeah. For a 2% failure rate, if we're making millions of these things out in the population, maybe we want to thicken something up or change the profile or increase the size of these tubes to lower this down to whatever's acceptable. But we can analyze all of those cases. So yeah, I think I'll leave it there. The first thing that I was going to talk about was why we should talk about fatigue and not just concentrate on FEA, which we'll have to do maybe another time.
Yeah, I mean, like fatigue, welds, connections, I mean, like in an hour. I mean, it's so hard to cover such an important topic in such a short time. So thanks, Mark.
It's like saying, tell me everything about FEA.
Exactly. Tell me, yeah. But that's a great reminder for me. I think in a future session we should talk about just connections in particular, talking about how do I create these line fasteners and these weld connections, because we just kind of really skipped over that, which is such a great aspect of the software to be able to create all these different types of connections and in particular welds, and then be able to use those welds in durability. So again, Mark, thanks, man. Appreciate it. Fun chat with you. Just everybody again, thanks for showing up. Thanks for listening. Last shameless plug or shameful plug. I don't know. It's probably shameful at this point, but please remember to like and subscribe so we can get out there, increase our exposure so that you guys can give us your feedback and let us know exactly what you would like to see next. And speaking of next, our next one is basically about how to make the ride a little bit less bumpy. So we're going to get into some fun stuff in the next episode. So please be sure to come back in the middle of December for the next session. So again, thanks everybody. Major thanks to you again, Mark. Appreciate it. And
thank you, everybody.
Yeah.
And yeah,
enjoy the rest of your
hope you survived the hour.
I did. Yeah. More coffee though.
It does help.
Yeah. Cheers. Thanks.
Thanks, everyone.